Good morning. Welcome to Krishna's class. We now go on to explore the inner structure of the concept of measures and integration. Now, what is fascinating is this, that we have a relation that you can establish between what are called linear functionals and the positive moral measures. Now, this is the main theme of big chapter that we are going to. The first of which we explore the concept of linear functionals on L1. And these are the preliminaries for essentially presenting the central result, namely the Riesz representation. One of the beautiful theorems in okay. So that's our plan. We begin with the concept of vector space. We will just quickly recall what a vector space is. So we are interested in complex vector spaces. V over C. C is the complex field that we take. V is a linear space over the complex field C. Essentially, the addition is a map from V cross V to V. And this is, of course, xy belonging to V cross V getting mapped to x plus y belonging to with some properties. What are the properties that we have? Before that, we also introduced the scalar multiplication structure, which we denote by dot. Later, we will skip using it frequently. So, this is a map from C cross V to V. Again, C cross V is alpha x getting mapped to the element alpha x belonging to. This is the scalar multiplication or the scalar multiplication. So these are the two maps that are related to the class of vector space. Now, what is the structure of this vector space with respect to this addition? Now, this defines an addition over V and a scalar multiplication along with C given by this. Now, what are the properties that she has got? The addition is commutative. It is associative. There exists an identity element zero in V such that then you have for every x belonging to V there exists minus x belonging to V such that x plus minus x equal to the identity. So what we have is this. You have x, y belonging to v. We have x plus y equal to y plus x. Then for every x, y, z belonging to v, we have x plus y plus z. This is associativity. X plus y plus z. And then you have x plus 0 equal to x. That is the identity element 0. Then you have for each x there exists minus x belonging to v, such that x plus minus x zero. Minus x is called the inverse element of x. So addition is not just an arbitrary addition, but constrained by these restrictions. So V has an addition defined on. Now what happens with the scalar multiplication? So this is about addition. Scalar multiplication that is x alpha x getting mapped to alpha x has the following properties. And what are they? There exists one see 1 times x equal to x. 1 belongs to C, that is a multiplicative identity element in C, and x belonging to. Then you have alpha beta x equal to alpha beta belonging to C. That means if you take beta x is an element of V, and then you can multiply with the scalar alpha. What you get is essentially take alpha beta, that is the product of alpha and beta in C. This will give you a complex number that multiplies x. This is true for every x belonging to E and for every alpha beta belonging to C. Now this is purely about the scalar multiplication. Now interactive properties. That means how the scalar multiplication interacts with the addition, okay, and vice versa. Properties. So you have what you call, this is scalar multiplication, and this first part is addition. The interactive properties are alpha with x plus y equal to alpha x plus alpha y, and alpha plus beta for alpha beta yeah. For every x, y belonging to V and alpha, beta belonging to C. Now these properties are now this is why I call it the interactive property is this. See, now we have defined this is purely about scalar multiplication. Okay? And this property is how your addition structure interacts with the scalar multiplication. Okay, so to add x plus y and multiply by alpha, this is the same as alpha x plus alpha y. And alpha plus beta of x is equal to alpha x plus beta x. Now, these properties, all these properties are satisfied, then B is a vector space. So you can see that the classical model for this is what you call Cn over C is a vector space over C with the usual standard vector addition and so on. Now, if you take all continuous functions over 0, 1 or for that matter any interval, complex value, on the interval 0, 1. Now with the usual addition and scalar multiplication, with usual addition, multiplication, is a vector space. Now it's a finite dimensional vector space. This is not a finite dimension. It's an infinite dimension. And there are several examples like and this I given just two standard ones which we will be using. Now we want to look at what is called a real vector space. Just a remark. So we take the associated field as R instead of C. Then you call it a real vector space. For example, when you take Rn over R, is an example. Rn over C you cannot take because a lot of things go wrong. Okay. But Rn over R is a See, Rn over R is a vector space. Even Cn over R is a vector space. But not Rn over C or R over C is not a vector space. That's something which you have to watch. So, and again in this example in C01, if you are confining yourself to real valued functions, then you will have to take the associated field as R. So that will be a real vector space. But that is immaterial. That is something you can always cope with as and when we come across that. But in general, we will be working with complex spaces. So wherever we make take a real vector space, we will make a special mention. Now we can so we now introduce what are called linear transforms. So let V and two vector spaces over complex vectors. Or in where situation comes, you also talk about real spaces. Let lambda be a map V such that so lambda is a map from U to V. Therefore, for x belonging to U is mapped to lambda x belonging to U. And is not any arbitrary map that we are talking about, but a map with this property. It's called the linearity. Lambda of alpha x plus beta y. You know that when x and y belonging to U, alpha x plus beta y belongs to U. So what is the image of under alpha of? Now this is defined as, this has to be alpha lambda x plus beta lambda y. This is for every x, y, alpha belonging to U, and of course alpha beta belonging to C. Then you say lambda is transformation from U and V are both vector spaces. As we can see. So such transformations are called linear transformation. I am not going into the details because these are all familiar things. Now we are for the moment concerned about a special type of linear transformation. Consider You know that C is a field and C over C is a one-dimensional vector space. So essentially, you can talk about linear transformations from V to C. So C over C is a one-dimensional vector space, and therefore it can take the value of the range or it can take the position of the range space, and you are talking about from a vector space to C, and lambda is assumed to be linear. Lambda linear. Then linear transformation V to C. Okay. Such linear transformations are given a special name. They are called linear transformations. When the range space is the associated field, then you say it's a linear function. Associated field. We call it a linear function. Now, the linear functions do play a very important role in what we are going to discuss. At the center of the Riesz representation theorem, we will have linear functions. Okay. So it's again a linear transformation. It's a linear transformation from one vector space into the other, but the range space being the complex field associated with that, or the real field associated with space, may you call it a linear? There is a special name so that we will be more frequently using this terminology. So we look at integration as a diagram. A typical example of a linear. On railroad. So let us work it out. So we take x mu be a measure space. Now we define L1 mu as a set of all f from x to c. It's a complex value x measurable and such that integral over x of mod f d mu. Then what you can prove is that, now here you see that he just make an observation. If f is measurable, mod f is measurable, and therefore integral continues. Now f measurable implies mod f is measurable. The converse may not be. It's quite easy to construct an example to show that the converse is not necessarily true. Okay. Therefore, integral we consider only those complex valued functions right. So this is the condition. So this is your L1 space. With designated type. Now L1 mu is called the Lebesgue integral functions. The vector space of Lebesgue integrable functions with respect to mu or what are called the sum of both them. These are the terminologies. So what you can prove is this, or immediately observe, is that L1 mu is a say linear force. L1. So for every element, you have a complex number as well. And this association is a linear map. Therefore, it's called a linear Krishna. Okay. So that's the one that we are interested in. Further, if G is a bounded, this can be relaxed. We'll talk about it. It's a bounded measurable function. Bounded measurable function on x. Well, complex valued bounded measurable function bounded measurable function of x. Then we can define the following on L1. An element of C. Or you call this define lambda G of f integral over x now you can easily show that lambda G is a on L1. That's very easy to verify. Okay. First of all, you see this is well defined. Why it is well defined? Because G is assumed to be bounded. G is complex valued, F is complex valued, their product is complex valued. It's a complex valued and G is measurable, F is measurable, therefore GF is measurable. So this is a measurable complex valued function. Therefore the integral is defined and this integral is certainly finite so that you go into C. Why it is so? Because you have the following, namely G is assumed to be bounded. This probably can be relaxed to bounded almost every. Okay. G is bounded, so let a bound of G on x. Then we have mod G. Mod G is just an origin. Now you see that integral over x which is finite. So therefore, this is well defined, right? And it's again a complex number. And therefore, you see that this is well defined, and then of course it is easy to show that. F2 and lambda g of therefore for any bounded function, complex valued measurable function on x. See, this is lambda g is a linear. So every complex valued bounded functions defined on x induces a linear functional on L1b. This is the outcome then. Okay. In fact, you can, as I said, you can generalize it by assuming that can slightly relax the restriction by saying that G is bounded almost. That we have seen the way in which we make use of such statements, and I am not going into details that you can. Okay. But this is just to get a view of what is. Okay. Now, what we are going to look at is the following. Okay. You have a linear function, and this is lambda g f. It's a complex number. Okay. Now that is defined for f. Yeah. Now g is the one that identifies. Now this can be related to a measure. Okay. So you can conceive this as what you call integral E f d mu can be conceived as integral x over t by defining mu as the measure of a measurable subset, mu is as integral over t okay. Therefore, d nu will become g d mu. I mean, these are all something that we have already looked at, and therefore, to see that this d nu can be replaced by g d mu, and you get the integral. So this is how g generates a measure. So see that you can associate g with, and we have already seen that mu defines a measure. For every bounded measurable with along with the given measure, a new measure is introduced. So you have got this association of G getting associated. Okay. So you have a new measure. So each G belonging to bounded measurable. So let me call this X. There is an associated measure. So this is A. The measurables. It's a new measure on. So G can be linked with B. Now, this kind of relations is what we want to explore in these. Let's take an example to get a feeling a much better feeling for what I said. Because of course we will be doing all these things in great detail when we look at the representation. So we will be trying to find out given a measure. You will be trying to identify with a G, appropriate G, so that lambda G is a bounded linear function on L1. So this is what we are up to. Okay. Okay. Now we want to look at a possible example. Okay. There's something that has gone wrong with the system. Stop here. So we'll consider the example next time. Okay. So we'll stop here. Yeah, just come back. Okay. So we start with an example to get a feel. So we take what is called X to be equal to I. We take I as an interval. You can even take I to be a special case I. You can take as we take I as 0. Now consider zero one. The set of all continuous complex valued functions on the interval 0. Now C01 is a vector space over the complex C. I mean, don't confuse between this C and this. This is continuity. This refers to the continuity. This refers to complex. This is the complex plane. Okay. Let so lambda f we define as follows. So we take the Lebesgue measure. So you take x, all Lebesgue measurables sets, and mu as a Lebesgue. So x equal to 0, 1, m and mu the Lebesgue measure. So what you have is lambda f d mu. You can write this is the same as integral 0 to 1 on our standard for continuous. So you see, since f is Riemann integrable, the integral is a should Riemann. So you recall we had some problems with the Riemann integration, especially corresponding L1 space that you can define was not complete. This was one problem. And to overcome this kind of difficulties, we went through a very lengthy exercise, very rewarding exercise, and we introduced what is called the concept of measure for subsets of R, and in this case subsets of the interval 0, 1. And what was the speciality that we sought? We sought that whenever the subset is an interval, the measures should agree with the length of the interval. That is, this AB is an interval an interval, then we required measure of the length of the interval. This is what we are after. So we wanted to, not only for intervals, we have a length now, we have a concept of length even for a larger collection of sets, so that it is not that all Riemann integrable functions alone can be considered for integration, but a larger class of uh, functions can be considered for integration. And this would facilitate ultimately the completeness of the L1 space. So this is the theme that we have considered earlier. So we make an observation. So lambda is a linear. And C0. C01 is a linear space. Further, we have this property, lambda f is greater than or equal to 0 whenever f is greater. So f is a continuous function which is non-negative on the interval 0, 1, then lambda f is greater than or equal to 0. Okay. So this is something about the technique. Now how do we connect the whole thing with the measure? The first job is, for intervals, we should recover the length of the interval from a measure. That's the first task. Now these are all finally going to be very rigorously handled, but at the moment we are just giving a sort of feeling for how we proceed further. So the first question is, can you the length of a that is the question. Or does there exist a linear function lambda on such that one can recover length of any interval a which is equal to b minus a from So we have to make this lambda such a way that this happens. So we'll start working on this. So we have done a job of constructing such a measure. So this will give you what is called the Lebesgue measure. This leads to so we are now seeking an alternative route for construction of Lebesgue measure. Is it possible to construct Lebesgue measure from a linear function? This is the question that we are asking. Now you see that lambda f defined as integral 0 1 f dx. It's a linear function. This we have seen. We shall use this. Consider all segments contained in diagram. And f belonging to C01 such that 0 f is non-negative and bounded by 1. So we are taking continuous functions on I such that f of x equal to 0 on the complement of on AB complement. That means whenever x does not belong to AB, f equal to 0. Fx equal to 0. Fx equal to 0. Now what one does is the following. Then we have lambda f is less than or equal to e minus. That is clear. For such f, this is so. Okay. Now we see that for the whole class of functions of this kind, for example, it is like this. Suppose this is AB. Now this is 0, 1. Now these are functions of this type. This is 1. So these are continuous functions of this type. Or even all non-negative functions of this kind. It's a continuous one. What happens is that you can take an extremal one easily like this. You can take the function to be something like this. Equal to 1 over here, over a interval a minus epsilon to a plus epsilon to b minus epsilon. We take f to be equal to 1 for x belonging to, and f continuous, f equal to 0 for AB. Now f is continuous on 0. So what do you have to do? You have to have 0 here, 0 here, and then patched up like this, which is possible. You have a positive, this is your a to a plus epsilon and b to b minus epsilon. See, there is a positive length available here. In between, you can patch it up with a continuous function so that the whole function on the interval becomes continuous. That is possible. That's a small exercise analysis. Okay. Now, for such functions, you can get a sequence. So, if you call this f epsilon, so you take lambda of f epsilon equal to is bounded by b minus a, and as epsilon tends to 0, this is something that you can always do. Okay. Now, therefore, you see that you can associate the given linear functional that we have defined here as generating the length of the intervals with appropriate actions over appropriate functions. Okay. So, that is something that we make. So, we are on the right. Okay. Now what we do is, we can, since it's a measurable function, now you have for all functions on f, or even for sets which are not intervals, you can generate this lambda and find it linear. I think I will just conclude this with this note that from lambda is a linear functional, you can actually associate that a measure, and this measure is what you call the Debye measure. Possibly because the system is now going for an update, I am forced to rather wind it up at this stage, and thank you very much.